All right, geometry friends, here we go. We're launching into 5.5, inequalities and triangles. And again, in this chapter, after looking at points of congruency and after looking at the mid-segment theorem, we're now looking at another quality of triangles, and that is kind of the relationships of their sides and their angles. And prior to that, though, our first definition is actually kind of a new type of proof, and it's called an indirect proof. And this is where you begin the proof by assuming that what you're trying to prove is false, and then showing that that will lead to certain contradictions or logical fallacies, so that therefore what you were trying to prove is impossible, so what you were really trying to prove must be true. Kind of like saying, if I'm trying to prove X, I'm going to start by trying to show that not X is true. And hopefully that leads me to some contradiction that therefore means, okay, actual X is in fact true. So let me try to give an example here with say you're trying to prove that an isosceles triangle can't have a base angle that is a right angle, okay? And so an indirect proof starts with saying, okay, let me take what it says. It says it can't have a base angle that is a right angle, and say, okay, well, no, it can. It can have a base angle that is a right angle. So let's prove that. Kind of like saying, let me try to prove the impossible to show that the other thing must be true. So what happens if an isosceles triangle has a base angle that's a right angle? Well, so that means you would have a triangle that would look something like this. You'd have a base angle that looks like that with a right angle. Now the key is it's a base angle, because if you know an isosceles triangle that typically has two congruent sides, it also has two congruent base angles. So that means if one base angle is 90 degrees, then over here, that means this base angle would also have to be 90 degrees. So you can see that that is not going to form a triangle. It'd have to be a square or rectangle or some other polygon. So there's no way you can form a triangle with two 90-degree angles. And that's what you have to try to explain in your indirect proof, is you'd say, once you try to state the opposite of what you're trying to prove, you'd have to say, not possible. A triangle can't have two 90-degree angles. You can see that visually from what I sketched there on the left, but you can also do it numerically, because all the angles of a triangle have to add up to 180. And if you have two 90-degree angles, basically you could say something like, 90 degrees of one angle plus 90 degrees of another angle plus whatever the third angle is, let's just call it X, that's guaranteed to be greater than 180 degrees, which again, that is not possible inside a triangle. So again, that therefore it means what I was originally trying to prove in the red is true. You can't have a base angle in an isosceles triangle that's a right angle. So that's an example of an indirect proof, and you'll be practicing some of those in the exercises as well as one of the questions here. Okay, so then the second definition is this angle size relationships within triangles. And what this basically is, very useful to know, is that the larger or smaller sides of a triangle correspond to the triangle's angles. In other words, the largest side of a triangle is always across from its largest angle. And then its smallest side is always across from its smallest angle. And then, of course, the intermediate, whoever's in the middle, is across from the intermediate angle. So let's just do it this way. If I were to say that, well, I'm going to just try to make it simple visual here. If say AB is my, I'm just going to make up a measurement, is 7, BC is 9, and AC is 11. Then I can immediately know the ranking or the size comparisons, not the exact amount, but the size comparison of my different angles. I know that, if this being true, I know that angle B is greater than angle A, which is greater than angle C. Okay, because again, the largest side here is across from B, so that means it must be the largest side. Smallest side, 7, is across from C there, so therefore B is my largest side, C is my shortest, and then A, being 9, is in between. And it works vice versa. It works the same way with degrees. It's just kind of like just a quick sketch. We've talked about right triangles, And we've always said in a right triangle, what's the longest side in a right triangle? Well, it has to be the hypotenuse. It would have to be this side right here. Well, we can see why that's true from an angle perspective, because this is 90 degrees. That's the largest angle in the triangle. There's no way the other two acute angles are the same. So therefore, this largest angle is equivalent to the largest side. Okay, and so then if I say I knew that this angle was 30 degrees, and I knew that this angle down here was 60 degrees, well, then I would know that this side is the second largest side and the bottom side is the third largest side. Okay, so that's all that the angle side relationship shows, is that they're proportional, or they correspond, not proportional, but they correspond to the larger side with the larger angle, the smaller side with a smaller angle. And yet there's more. There's also the triangle inequality theorem that states that the sum of any two sides of a triangle is greater than the third side. So that you cannot draw a triangle where you add up two of the sides, and we're not talking about the Pythagorean theorem where we square and add them. No, just the sides themselves. If you add up two of the sides, they must always be greater than the total of the third side. You could just try this out. Get out a ruler and figure out, okay, I'm going to draw a side here and a side here, and then I'm going to draw a side that's longer than those two sides combined. It'll never work into a practical triangle. And so we have an example here of just a 3, 4, 5 triangle. A way that you could check and say, okay, is this triangle possible? Is you would see if I add up any two, of the sides, like say if I had 3 plus 4, okay, that's going to be 9, or I'm sorry, 7. That is, of course, greater than the third side remaining, 5. So that works. But it has to be all combinations. So now let's go, what about 4 and 5? Well, okay. So 4 plus 5, that's going to be 9. And that, of course, is greater than the other side, 3. All right. And then we need to check the last combination, which would be 3 and 5. So 3 plus 5, that's 8. And that is greater than the missing side, 4. So in other words, we know that these are possible measurements of sides of a triangle. An example of where that doesn't work is another one here below. So say you were given and said, oh, you have a triangle that has sides 4, 6, and 11. Well, let's check. Let's start with the top two sides. 4 plus 11 is 15. Is that greater than the third side of 6? Yes, that's perfectly fine. What if I do 4 plus 6? That's 10. Is that greater than the third side, 11? No, that doesn't work. So there's no way that this is a possible combination of sides for a triangle. Whereas up here in the blue, we would say, yes, that is a possible combination. So again, in other words, or say it again, the sum of any two sides of a triangle, any kind of triangle, not just right triangles or any particular type, must be greater than the third side. So let's take a look at some of the questions from the book, just explaining this. So number 1 says, it's what we were just talking about, could a triangle have side lengths 3, 5, and 7? Well, let's just run through the various scenarios and see. And you could do it probably faster than I can, but I'm going to kind of just do it methodically. So let's see, 3 plus 5, that's 8. Is 8 greater than the third side, 7? Yeah, that's okay. Okay, so how about 3 plus 7? Is that greater than the missing side, 5? Well, let me keep my format consistent. That's 10. Is 10 greater than 5? Yes, that's okay. And then I could go, okay, how about 5 plus 7? 5 plus 7, that is 12. Is that greater than the missing side, 3? Yes. So boom, all 3 combinations check out. So our answer here would be C, senor. Yes, that is very doable. Okay, how about in the book we're just doing, again, we're on page 336. Or no, this is actually from the assignment I've given you. How about if it was 3, 5, and 9? Well, let's check it out. First 2, 3 plus 5 is equal to 8. Is 8 greater than 9? Okay, right off the bat, we have a problem. The sum of the two sides is not greater than the third side. So immediately I know these are not possible measurements for a triangle. No, very sorry. Okay, how about second question? Similar, but another slightly different application. Is it says the lengths of two sides of a triangle are 6 centimeters, and 11 centimeters. Find the range of possible lengths for the third side. So now we're not trying to find a third side, but we're trying to see what is possible. How big or small could the third side be? Well, again, the third side cannot be greater than the combination of these two sides. So if 6 plus 11, that's 17. 17 has to be greater than our missing side. Or I'm sorry, our missing side would have to be less than 17 because it can't be equal to 17 and it can't be bigger. So therefore, our other side has to be smaller than 17. Now that's pretty good. That's mostly a range, but then you have to ask yourself, well, is there a minimum? So it has to for sure be less than 17. How small can it get? Well, because we're talking about sides of a triangle, it would have to be greater than 0 because you can't have a side length of a triangle that's less than, that's negative or non-existent. So when you're talking about a range, and again, I could write this, switch the order from smallest to greatest, but the side range would be, it has to be bigger than 0, because it can't be nothing, but it cannot be bigger than 17, because then it would exceed the sum of the other two sides. And so there we go, we can actually find a range of possible side lengths for that triangle. Alrighty, and then takes us to number 3. So number 3, we're actually solving 2 problems out of the book. Page 336, number 2 and 4. Number 2 is an indirect, number 2 is actually a indirect proof from the book. It says write an indirect proof of each statement, which says a scaling triangle cannot have 2 congruent angles. Well, you kind of get a bit obstinate and argumentative with an indirect proof, and you get to say, okay, no, it can. What if a scaling triangle can have 2 congruent angles? So, for example, I can draw a scaling triangle, and I'm going to say, well, you know what? It's got, this angle is 50, and this angle is 50. Okay, and that would mean the other one up here is 80. All right, and so that's my scaling triangle. It can be like that. And then you go, wait a minute, why not? Well, because if I have 2 congruent angles like that, what we've learned is that means I also have 2 congruent sides. 2 congruent sides. As we're learning, there's a relationship between the angles and the sides. They're proportional. And we've already learned that when you have an isosceles triangle, you have 2 congruent angles as well. So what does that mean? Oh, problem. You can't have a scaling triangle because what type of triangle is this? This is a isosceles. And so that's the kind of logical inconsistency you run into with an indirect proof. So I would say 2 congruent angles, 2 congruent angles makes a triangle isosceles. Okay, so therefore, a scaling triangle, not can, but can't. Alex, that's a terrible can't. Triangle can't have 2 congruent angles because then it would be an isosceles. So again, practicing indirect proof by arguing the opposite of the conclusion you're really trying to prove. Works lots of types of arguments, not just even math proofs. Alrighty, and then number 4, real basic, trying to show the relationship with the corresponding relationship between angles and sides, is it just says write the angles in order from smallest to largest. And how would you know that? Well, again, what that states is simply you just side length. So there it is. There's the smallest one. So that means that angle R must be the smallest. Angle R, whoops, followed by the next number, 45, so angle P, followed by the largest, 57, which is angle Q. So really simple, but trying to get the basics here on your notes, that the larger the angle, or larger the side, or either way, larger the side, the larger the angle, larger the angle, the larger the side, and smaller. All right, so that's 5.5, triangles and inequalities, and I hope you had as much fun as I did. All right, see you soon.